Hello, let's look at horizontal asymptotes today in AP Calculus, or just any calculus, I guess. And we're going to look at asymptotes from the perspective of limits as x goes to infinity. I will use a sheet on this, and it'll be like a fill-in-the-blanks guided notes sheet. So if you are a random person who found this on YouTube and you want to print that sheet, you can go to this bit.ly link down here, HA limits, and moving on. So let's look at horizontal limits, and these are limits as x is going to either infinity or in negative infinity. And if you think about what's happening as we go forever to the left or forever to the right, we are describing the end behavior of a function. And so if you do find the limit as x goes to either positive or negative infinity, this is kind of a poor notation right here because you can't approach both positive and negative infinity simultaneously. So that was just me being a little bit lazy. But if you do get a real number answer for that limit, then that means that your function f of x has a horizontal asymptote at that value. Because what that means graphically, let's just say going to infinity, we do equal L, and let's just pretend L is 3. Well, if L is 3, that will be some y value of 3. And I could be doing anything over here towards the y-axis. I could be going up and down, and who knows what I'm doing over here. But as I keep working my way to the right, I'm going to have to level off and approach that value of 3, which is why we would have a horizontal asymptote at that value of L, whatever L is. Now, one good thing about horizontal asymptotes is in pre-cal and algebra 2, you very well may have learned a very quick and convenient way to find horizontal asymptotes. You probably did not do it in the context of limits. If you had a great teacher, I hope they did show you that, but you probably did. You probably did it without limits. And so, if you have any function where it is a fraction, it is a rational expression, and f and g are both polynomials. That means x to an integer power, no square roots, no trig, no exponents, no logarithms, things like that. So just nice, clean polynomials. You can find the horizontal asymptotes of that function by comparing the degrees of the numerator and the denominator, which are f and g in this example. If your top degree is bigger, then you do not have a horizontal asymptote. I'm going to come back and talk about that in just a second. If the bottom degree is bigger, you may remember that means your horizontal asymptote is y equals 0. So you will approach the x-axis as you go to positive and negative infinity. And if the if the top and bottom degrees are equal, you find the horizontal asymptote by dividing the leading coefficients of the numerator and the denominator. So I want to go back and talk about this non-existent asymptote here for a second. If you do not have a horizontal asymptote, then that means that so this is if no horizontal asymptote. If you do not have a horizontal asymptote, that means your function does not level off. So as we keep going over there to the right, your function's not leveling off at a particular y value, which means if you aren't leveling off, you are either going up or you are going down forever. And in the context of limits, if you were going up or you were going down, I personally would much rather you say that the answer to the limit would equal infinity or negative infinity, to indicate that, yes, there is no horizontal asymptote, the limit does not exist, but we can specify in which way the function is going due to the lack of a horizontal asymptote. So let's go on. Let's look at examples, and we're going to do these the pre-cal way. We're going to compare degrees on top and bottom and knock these out relatively quickly. So on number 1, x is going to infinity, and I probably should have stressed earlier, make sure x is going to infinity. Some students love these rules so much that they will immediately start comparing degrees on top and bottom, and they will fail to realize that x is approaching 2. Well, if x is approaching 2 instead of infinity, well, then you would have to do the substitution. You may have to factor. There are other techniques. So double check and make sure that x is going to either positive or negative infinity, as it is on number 2. And if that is the case, then you can compare the degree on top and bottom. Here, the bottom is bigger than the top. And if the bottom is bigger than the top, then the answer to this limit would be 0. Now, the limit answer is 0. If you are asked to find the horizontal asymptote, then you would say the horizontal asymptote is the equation y equals 0. Number 2, x is going to negative infinity. But in the case of polynomials and rational expressions, we don't need to worry about that just yet. I still am going to compare degree on top and bottom. Top degree is larger than the bottom. And if the top is larger than the bottom, then that means the limit does not exist. There is no horizontal asymptote. And that means I can indicate whether this is going to infinity or negative infinity. I will come back to that in just a second. Let's knock out number 3. X goes to infinity. My degree on top is 3. My degree on bottom is 3. Those are equal. So if the top is equal to the bottom, you divide the leading coefficients. And the leading coefficients in this case are negative 5 in front of the x cubed and 2 in front of the x cubed down here, which means your horizontal asymptote would be the equation y equals negative 5 halves. Okay, so let's go back to number 2. And if there is no horizontal asymptote, then that means on number 2, as I work forever to the left, I'm going to negative infinity. I'm either going up or I am going down. And to find out which one of those two we are approaching, what we're going to do is look at the high power terms, because that's what's driving the end behavior, the high power terms. So we're going to ignore the 12x and the 7. And I'm going to think, what if I plug in a huge negative number? And it doesn't even have to be huge, just any negative number. If you plug in a negative number for x, what happens with 3 times a negative number to the 5th and a negative number squared? Well, if you raise if you raise a negative number to an odd power, you get a negative result. If you square a negative, you get a positive result. A negative divided by positive would be something less than 0, which means the answer to the limit would be negative infinity. So we now know that we're looking at this situation, not that one. So there are the memorized rules where you compare the degree of top and bottom, and that's ridiculously convenient. I'm not a big fan of memorization math, but these techniques, that memorization approach is so efficient. I recommend you remember those. However, if you are bad at remembering little shortcut rules like that, there is pretty much a one-size-fits-all approach that works for all 3 situations. And so the good thing is it's just one approach and it works for all 3. The bad thing is it takes a little bit longer. And this will work anytime that your numerator and denominator are polynomial-ish. Now I'll put that ish at the end because this technique does work if you happen to have like a square root of x or things like that. But as long as you have x to number powers and you're not looking at exponentials, logarithmic, trig, things like that, then this technique can work. And what we do is we look in the denominator and we find the highest power of x that is in the denominator, and we will divide every single thing in the fraction by that high power of x. And so if my denominator has an x cubed, and that is it, I'm going to divide every single term by x cubed. Divide by x cubed, squeeze a divide by x cubed here. And then I will reduce each one of those. So I have the limit as x goes to infinity. The numerator, 3 over x cubed, does not reduce. The 5x cubed over x cubed is just negative 5. 2x cubed over x cubed is 2. And 12 over x cubed does not reduce. And in these problems, we end up with only 2 places that the x can impact. If x is going to infinity, we will only impact the 3 over x cubed and the 12 over x cubed. Let's look at this 12 over x cubed. And you're not supposed to plug infinity in for x. It's not a real number. So substituting infinity for x kind of fudges the rules of mathematics here. But this is essentially going to be 12 divided by a ridiculously huge number. And if you pulled out a calculator and you punched in your calculator 12 divided by 100, you would get like 0.12. If you divided by 1,000, you would get 0.012. If you divide by 10,000, you get 0.0012. And as that denominator gets larger and larger and larger, and especially as we go to infinity, any constant divided by infinity will always go towards 0. The same thing's going to happen on top. 3 divided by infinity cubed, that's going to go towards 0. And so the answer to this limit would be 0 minus 5 over 2 plus 0, which is the same thing as negative 5 halves. And that is the same thing we got. I'm going to go back. I don't know if you noticed, number 4 here is the exact same as number 2. And we did indeed, as number 3. And we did indeed get the same answer of negative 5 halves. Let's look at another one. So x is going to negative infinity. And this one is number 2, I believe. So if x is going to negative infinity, that is infinity. I'm going to divide by the high power of x in the denominator, which is x squared. So everything's going to get divided by x squared. And we will reduce each one of these fractions. And when I reduce those, we get the limit as x goes to negative infinity of 3x to the fifth over x squared is 3x cubed. 12x over x squared is 12 over x. X squared over x squared, and 7 over x squared. And then we look and see what x at approaching negative infinity can still impact. Any constant divided by infinity will go to 0. That's going to go to 0. That's going to go to 0. However, I still have this. This one right here is 3 times negative infinity cubed. If you cube infinity, it's just going to get even larger. So it's still infinity. But if you cube a negative, that will remain negative. So 3 times an infinitely large negative number cubed will go towards negative infinity. So what we have here is negative infinity minus 0 divided by 1 plus 0, which means the answer to this limit is going to be negative infinity divided by 1 or negative infinity. So there's our answer to this one. And if you go back and look at number 2, you'll see that that is the same answer we got the first time we worked this limit through a slightly different method. Okay, let's ugly it up a little bit. What if we don't have polynomials? What if we have a square root? Well, that is not going to change my approach. I still want to look in the denominator and find the highest power of x, and I'm going to divide everything by that high power of x. And you may be looking at this and thinking, well, the high power of x is x squared, but that is a square root of x squared, which would be the same thing as x. It will be the same thing as x. So while that looks like an x squared, I'm actually going to divide everything by x to the first. Divide by x, divide by x. In the denominator, what I divide by in the denominator, I like it to resemble what I am dividing it into. So instead of dividing 9x squared and 1 individually, I'm going to divide that whole radical by an x, but my x is going to look like this, the square root of x squared, because I want it to work nicely with what I am dividing it into. Now, the numerator is not a problem. Let's go ahead and clean up the numerator. And truthfully, the denominator should not be too bad. So x divided by x is 1. 2 divided by x does not reduce. In the denominator, if you were doing a fraction divided by a fraction, you can take that thing, I'm going to come over here, and you can make that one big honking fraction of 9x squared plus 1 over x squared. And then what I'm going to do is use something that I call an STD. We're looking at an STD, and if you have an STD, you want to address it. You don't want it to linger. And in my class, STD stands for single term denominator. So if you have a single term denominator, an STD, you want to get rid of it. And we do so, well, a lot of times you want to. You do so by dividing each term in the numerator by the denominator. So if it's 9x squared plus 1 all over x squared, I can split that into 9x squared over x squared plus, and then I will do 1 over x squared. So we get that 1 over x squared. And then I can reduce those individually. And so that square root becomes the square root of 9x squared over x squared, which is 9, 1 over x squared, which is 1 over x squared. And then finally, I can look at this limit as x goes to infinity. I only have 2 x's remaining, and they are in the denominator. So 2 divided by infinity, that will crash to 0, as will 1 over infinity. And the answer to this limit is going to be 1 plus 0 over the square root of 9. And if you are super smart, you will know that the square root of 9 is 3. So there's our answer for this one. Moving on, moving on. 2 more. And these are going to be a little bit of a beastly problem. I was hoping to finish this up in 15 minutes. It doesn't look like that's going to happen. So this one is probably going to be the one that requires the most amount of work because I don't have a fraction. If I have x going to infinity, I would really prefer to have a fraction. And so what I'm going to do here to force the fraction is I'm going to put this over 1, and we get to multiply the numerator and the denominator by the conjugate of that numerator. So I'm going to multiply by 9x squared plus x. We don't change the sign under the radical. We change that sign between the radical and 3x. So there's that conjugate. In the denominator, I'm going to multiply by the exact same thing. Don't forget to do the denominator as well. And well, the denominator is going to be easy because that's just 1 times a bunch of stuff. So that's going to be the square root of 9x squared plus x plus 3x. And then in the numerator, we have to expand these conjugates. And the beauty of conjugates, we only have to do first times first minus last times last. And root 9x squared plus x times root 9x squared plus x is 9x squared plus x. Negative 3x times positive 3x is negative 9x squared. And if you look at that numerator, the 9x squareds cancel out. So now I will cancel those 9x squareds, leaving me with just the x. The denominator is root 9x squared plus x plus 3x. And after all of that work, I finally have a limit that has x's in both numerator and denominator, and it kind of resembles the one we just did. So we're going to do the exact same trick. I'm looking in the denominator, my highest power of x, I see x to the first and I see an x squared, but that's the square root of x squared, which is really just x to the first. So I'm going to divide everything by x to the first, divide by x to the first. Whoops, that's not one. Divide by x to the first, except the square root. I'm going to do the exact same thing I did last time. I'm going to divide by the square root of x squared. And then that's going to give me the limit as x goes to infinity. Numerator is just 1. The denominator, 3x over x would be plus 3. I still have the square root to worry about. And we can STD this one. 9x squared over x squared is 9. X over x squared is 1 over x. And so we're doing that exact same trick. I'm taking 9x squared and dividing it by x squared. And then I'm taking the x and dividing it by x squared to get that. And after all of that work, I only have one place now that x is impacting. As x goes to infinity, 1 divided by x would be 1 over infinity. That's going to crash to 0. And we finally have our answer of 1 over the square root of 9 plus 0 plus 3, which ultimately is 1/6. So there is that one. Whew. And one more. So let's look at number 8. This one's already a fraction. X is going to infinity, so I'm already set to choose my high power of x in the denominator. And I'm looking and I see x to the first and a square root of x squared, which is also x to the first. So I'm going to divide by x to the first on everything, on everything, on everything. And my square root will be divided by the square root of x squared. Except for this problem, and this is a very tricky step to remember. It's not hard to do, but it's hard to recognize, or it's easy to forget to do this. If x is going to negative infinity, that means my x's are negative. My x's are negative. So when I divide by an x here, I'm dividing by a negative number. This 3 over x, that's a negative. This 6x over x, that's a negative. Those are fine because I want x to be negative. However, when I divide by the square root of x squared, when I squared that x, I turned it positive, and that becomes a problem. And so we need to think about the square root of x squared and how that is impacted by negative x's. And we are working with the property that the square root of x squared is equal to x. Well, let's just test that formula out. Does the square root of x squared equal x? Well, it does if x is a positive number. If I plug in 7 for x, then I'll have the square root of 7 squared, and I'm going to replace the x with a 7. The square root of 49 is 7. That works. However, what if x is negative 7? If x is negative 7, well, then when I substitute negative 7 for both of these x's, I get the square root of negative 7 squared is equal to, and I'll replace that x with a negative 7, and this ends up with the square root of 49 is equal to negative 7, and that's just not true, is it? We get 7 equals negative 7, and that's not true. So when we are dealing with negative x's, so if x is less than 0, we tweak this property. Whoops, I didn't mean to do all that. We tweak this property that says square root of x squared is equal to x, and we fix it by putting a negative in front of the square root. because now if I put a negative in front and I carry that negative down, we end up with a true statement that -7 equals -7 in this one example. And so right here, when I divide by the square root of x squared, I need to divide by the negative square root of x squared. And like I said a minute ago, very easy to do. It's easy to stick that negative in there, but also easy to fail to realize that it is necessary. So now I have the limit as x goes to -infinity. We'll reduce each of these 2x over x minus 3 over x, all divided by the square root, except I almost made a mistake. The square root of 16x squared over x squared would be 16. 2x over x squared is 2 over x, but that was a positive root divided by a negative root. That negative stays here. 6x over x is 6. And finally, as x is going to -infinity, these constants divided by x will crash to 0. And we are left with an answer of 2 minus 0 over negative square root of 16 plus 6, which ends up being 2 divided by -4 plus 6. That ultimately reduces to just 1. And I really did not want this to end up being 21 minutes, so I apologize for that. And I even had one more that I wanted to do. I'll put it up here. It's a good question. And I'm simply going to say that if you're ever asked to find all horizontal asymptotes, you must consider x goes to +infinity and -infinity, because this is an example of a function that has two different horizontal asymptotes in each direction. But I've already pushed this video too long, and I don't feel like going any further here.